Hello. In this video, we want to look at some of the tables that you'll see in the book. So the first one that we're going to look at is the existence of limits. So the limit of f as x approaches a may not exist. We've seen that a couple of times already. So if f of x becomes infinitely large in magnitude, positive or negative, as x approaches the number a on both sides, we brought the limit as x approaches a of f of x equals infinity, or the limit as x approaches a of f of x equals negative infinity. In either case, the limit does not exist. Now, what's happening here is something like this. We say that if you see a table or if you see a graph and it looks like this, where you have a vertical asymptote, and this is going up towards infinity that way and that way as well from both sides. If this is a, then the limit as x approaches f of x as the limit as x approaches a of f of x is infinity here. The limit does not exist still, but it's going up to infinity on both sides. The reverse can happen as well. If it's going down, we just say the limit is equal to negative infinity. Still, the limit does not exist, but we say more specifically that it is equal to negative infinity. If f of x becomes infinitely large in magnitude as x approaches a from one side and infinitely large in magnitude in the negative direction as x approaches a from the other side, then the limit as x approaches a of f of x does not exist. Now, what's happening here is something that looks like this. Again, here is a. If the function is doing something like this, where it's going up to infinity on one side and down towards negative infinity on the other, then therefore the limit simply does not exist. We can't say if it's equal to infinity or negative infinity, we just say that it does not exist. Now, for this last one here, if the limit as x approaches a from the left-hand side of f of x equals L, and the limit as x approaches a from the right-hand side of f of x equals m, and these two limits are not the same thing, then the limit as x approaches a of f of x does not exist. So this one is another time when it does not exist. Now, what's happening here is something like this. Let's say you have a function that looks like this. So if this right here is a, notice that the limit as x approaches a from the left is this value. The limit as x approaches a from the right is this value. These are not the same values. Therefore, in this case, this is when the limit would not exist. Okay, this is for the existence of limits. Next, we want to look at some rules for limits. There are a lot of them, and I'll be honest with you, it's really not that difficult once you understand that really what this is saying is that if you can take the limit by just plugging in the function value, or plugging in the value that you see for here, then that's all it is, really. That pretty much covers all of this. So let little a, capital A, and capital B be real numbers. Let f and g be functions such that the limit as x approaches a of f of x equals a, and the limit as x approaches a of g of x equals b. In other words, the limit of f is a, the limit of g is b. If k is a constant, then the limit as x approaches a of k is equal to k, and also the limit as x approaches a of k times f of x is k times the limit as x approaches a of f of x, which gives you k times f of a. In other words, you can just plug in the a into here. Same thing for a sum or difference. So the limit of a sum or difference is the sum or difference of the limits. And for a product, so the limit of a product is the product of the limits. And for quotients, the limit of the quotient is the quotient of the limits, provided that the limit of the denominator is not zero. In other words, if you can plug in a into both the numerator and denominator, then it works out pretty well. Number 5, limit if p of x is a polynomial, then the limit as x approaches a of p of x is p of a. This is why we love polynomials. Basically, you just plug in the function value into the polynomial, and that is what it's going to equal. 6, for any real number k, the limit as x approaches a of f of x to the kth power is the limit as x approaches a of f of x all to the kth power, provided this limit exists. So basically, the limit of exponential is the limit of the function to the exponential power, basically. So the limit as x approaches a of f of x equals the limit as x approaches a of g of x if f of x equals g of x for all x not equal to a. For any real number b greater than 0, the limit as x approaches a of the exponential b to the f of x equals b to the limit as x approaches a of f of x, which is just b to the 8th power. Again, just plugging in the value. And the same thing with logarithms, that it'll happen as well. So really what all these rules for limits are telling us is simply that if the function is, well, kind of put this in quotes here, well-behaved, then you can just plug in the function value to get the limit. That's really all it is, and then once you've accomplished that, the rest of limits is just figuring out what to do when you can't just plug in the a value. And I've already shown you several ways of handling that, and one of those was by looking at a table and saying, what's the function doing as x approaches a from the left, and then from the right, and then are they the same thing? And that's pretty much it. We'll also have some more ways of doing this with, shall we say, more of an algebraic way of doing it, and that'll be fun as well. Alrighty, well, I believe that's it for this video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.